Welcome everyone. My name's Nathan Ellis and I'm going to be talking to you for the next few minutes on gate drive power delivery techniques. But to first just give you a little bit of background, I'm talking to you today from Northern California, just across the bay from San Francisco. Here I work as a postdoctoral researcher within the Palawa research group, where we are investigating a number of exciting topics within the field of power electronics. We are perhaps best known for our contributions to the relatively new and exciting field of hybrid switched capacitor converters, and multi-level converters, and a number of energy applications, including photovoltaics, data centers, EV, and even some consumer products. It is my pleasure to present here at WiPDA, given that wide bandgap devices such as gallium nitride have really enabled us to perform some cutting-edge research, and as such we feel as though we've been on the front line in figuring out how to use these new devices most effectively and reliably. Today I'm going to focus on a particular problem that for us comes up time and time again, namely that of delivering energy to the many high-side gate drivers within these more complicated power converter topologies. In this case, we're going to use the flying capacitor multi-level converter as an example. Now, this is a very versatile topology that allows for an approximate n² reduction in the size of the magnetic components used, where n is related to the order of the surrounding switched capacitor network. If you would like to learn more about this fascinating topology, please see the following article. However, here I would like to draw your attention to the large number of independent voltage sources providing power to each of the gate drivers. Now, there are a number of ways to produce these supplies, the most conventional of which being to use a fully isolated supply for each of them. However, this approach comes with several drawbacks, including a greatly increased overall converter volume, high cost, and moderate efficiency. Further commercial efforts have produced more compact power delivery solutions, but the reduced magnetic volume inevitably degrades performance while maintaining high cost. So in this work, we instead take a look at some non-isolated approaches, the most well-known of which being the diode-based bootstrap. This approach is widely used in half-bridge structures where, upon activating a low-side switch, both bypass capacitors share a common bottom plate and charge subsequently flows through a bootstrapping diode to increase VDD2. However, do note that due to the diode's inherent forward voltage drop, VDD2 will remain slightly less than VDD1. However, this difference is often deemed negligible even when using wide bandgap switching devices. The same can not be said when this bootstrapping technique is used repeatedly. Here, forward voltage drops will continue to accumulate. In this simulation, we see that while the lowest gate driver is provided with 16 volts, the last gate drivers in the chain only receive about 6. Of course, this is unacceptable for most applications. To surmount this, recent work here at Berkeley has suggested using local regulation within each gate driver. This works very well with dedicated linear regulators providing consistent voltage supplies to all devices. However, since this regulation is very lossy, we see somewhat poor efficiencies in practice, although that's not to say that this is without merit. Prior work using this technique has shown a 50% reduction in overall converter volume, and while efficiency is poor, it can still be better than compact isolated power delivery. Moreover, production cost is greatly reduced. To take this work further, we will now introduce the concept of synchronous bootstrapping. The idea here is to replace our diodes with active switches. These transistors do not have a forward voltage drop, and so we can expect improved performance in practice. The question then becomes how to generate appropriate signals to control these active devices. Ideally, our gate-to-source voltages would look similar to those depicted. Here, our boot FET only turns on within the time interval that our primary FET is turned on, perhaps with some margin for reliability. Should our bootstrapping transistor ever turn on outside of the specified interval, we would risk a potentially catastrophic surge of charge flowing back down towards the low side supply, similar to shoot-through when there is insufficient dead time. The most well-known approach to generate appropriate signals is that proposed by EPC within the last few years. Rather than generating these ideal signals exactly, this solution approximates these waveforms using an introduced RC time constant to delay the boot FET's rising edge. This rising edge delay is set by resistor R1 and the internal CISS input capacitance of the boot FET itself. Here, capacitor CP is large, storing a voltage of VDD, and simply acts as a level shifter. During the falling edge, resistor R1 is bypassed by diode D1, and the boot FET turns off at approximately the same time as the primary FET. Our research group has validated this approach with the depicted results showing a greatly reduced voltage droop. Rather than requiring 16 volts on the input, here only 6 volts is required to provide at least 5 volts to all gate drivers across a range of operational duty cycles. However, this approach has limitations at high switching frequencies where the RC delay proves to be problematic. To understand this, next we will magnify the highlighted rising edge and use some slightly more accurate waveforms. Zooming in, we note that the boot FET's gate, depicted in red, begins rising at the exact same time as the gate of the primary FET, depicted in yellow. However, the RC delay must be long enough such that the boot FET signal does not reach its turn on threshold until the primary FET has fully turned on. To do otherwise would risk the shoot-through condition described earlier. Unfortunately, this reduced slope continues for the remaining rise time, with mboot not reaching its minimum RDS-on until much later. Ideally, we would prefer our boot FET to be driven with a gate signal that turns on sharply and as soon as possible, as is depicted here in green. By implementing this well-controlled and sharp gate drive signal, we would maximize our conduction duration and use a minimum RDS-on for as long as possible. Both of these effects should serve to reduce our voltage droop even further. Here, we note that this more ideal bootstrap signal can be easily generated by making a very minor modification to the well-known classic non-overlapping clock generator. This circuit is commonly used within fully integrated half-bridge gate drivers to produce well-controlled dead time intervals. In this work, we designed a small daughter board that leveraged the internal dead time circuitry of an existing dual gate driver, depicted here as U2, along with a buffered signal inverter, U1. The result is a very small driver board that is amenable to complete integration using existing IC technologies. 2 discrete tuning resistors are used here to precisely set the delays between pairs of rising and falling edges, with measured waveforms verifying intended operation. The components used are as shown. These daughter boards were then used to construct an FCML converter with full synchronous bootstrapping capability. But before showing you the results, I would like to introduce one more very interesting capability of synchronous bootstrapping, which has not yet been widely discussed. This is a capability that I like to term bi-directional charge flow. To understand this, first consider the diode-based Cascaded Bootstrap shown earlier. In this case, charge can only flow from one gate driver to that situated above it. That is, charge must flow in an upwards direction. Similarly, when using synchronous bootstrapping transistors, charge can also flow in an upwards direction, but since transistors can conduct charge in either direction, dissimilar to diodes, charge can also flow in a negative direction, from a high side driver to that situated beneath it. To avail of this capability, in this design we chose to include a small charge pump which produces a 5-volt supply that is instead referenced to the high side input line voltage. In this case, charge can be delivered upwards through the chain, as is expected. However, charge can now also be supplied from the high side of the bootstrapping network. This serves to greatly decrease the bootstrapping network's impedance since the chain's path length is approximately halved. As a result, voltage droop is decreased even further. The plots on the right depict measured gate drive supply voltages when power is delivered either from a ground-referenced supply, a line-referenced supply, or both simultaneously for best performance. As shown in the top right figure, at a converter duty cycle of 50%, a maximum voltage deviation of about 100 millivolts is observed across all gate drivers when using the proposed technique. A maximum voltage droop of 160 millivolts is observed across a wide duty cycle range of 15 to 85%. As such, the need for local regulation is entirely eliminated, even when using sensitive, high-tolerance switching devices such as gallium nitride. Finally, here we show a photograph of the entire system alongside a measured efficiency curve and table of components. All data was taken at a very high switching frequency of 500 kHz, further emphasizing the significance of the results shown thus far. We began this presentation discussing conventional gate drive power delivery approaches and highlighted the cost, volume, and efficiency limitations of magnetic approaches. We then expanded our search into recently published non-isolated techniques which have shown significant potential. Developing on synchronous bootstrapping methods, here we have demonstrated a technique which is compatible with existing IC technology while delivering significant performance benefits. By maximizing the conduction duration and introducing bidirectional power delivery, voltage droop is made negligible and the need for local regulation is eliminated despite operating at very high switching frequency. As such, we have arrived at a gate drive power delivery solution suitable for high-order topologies, including flying capacitor multi-level converters. Furthermore, it yields a very high gate drive efficiency while improving significantly on volume and cost. Thank you for listening, and I would love to hear any of your comments or questions.